Up until this point, we have been looking at atoms and molecules on a very small scale, so like one atom at a time or one molecule or something like that. Chapter 6 starts to look at things on a much larger scale. So for example, to get enough of an atom to be able to put it in your hand and see it and measure it, you would need a few billion atoms. So just to cover, say, a 1-inch line, you would need a few billion atoms or molecules of something. So we need to figure out a way to estimate a large number of atoms. So again, if you did have in your hand a sample of carbon atoms, we would want to know how many carbon atoms you have. Because if you kind of recall from chapter 5, when we built different molecules, they all combined in certain ratios. So we need 2 of these for every 1 of these. So that's going to be important that we know how many atoms of something we have. Okay, so let's look at how that is done in chemistry. We're going to estimate a large number of objects, like atoms. So here we have a 5-gallon water jug filled with pennies. So propose 2 methods to find the number of pennies in the container. Okay, so there's a few ways you could do this. One, you could do the painstakingly long method of 1. You can just count them. So that's going to take a really, really long time if you dump those pennies out and just try to count them. So what we're going to concentrate on this chapter is what's called, we're going to count by weight. So we're going to count by weight. Okay, so if you recall back to chapter 4, we looked at the atomic mass of elements. So for example, aluminum here, aluminum has an average mass of 26.98 for atomic mass units for 1 atom of aluminum. So we know essentially the mass of 1 aluminum atom as, 26.98 atomic mass units. So if we know, say, the mass of 1 aluminum, it doesn't stand to reason that we can extrapolate this to a large sample. So that's what we would do for this jug. So we would get the mass of 1 penny. Okay, so if we had the mass of 1 penny, then we can take the mass of this whole group of pennies and just do a simple ratio to see how many pennies we would have in this jug. Get the mass of 1 penny. We'd get the mass of our jug of pennies. Then we can just divide them to get the mass of the pennies, or to get the number of pennies that we had in this container here. So we would be counting them by weighing them. Again, since we know the mass of 1, if we get this whole entire mass here, if we just divide, then we can get how many pennies are in here. Okay, so propose a method to determine how many carbon atoms are present. So we could use the same thing that we did with our pennies for a sample of carbon. So we do know that 1 carbon atom has a mass of, if we look at our periodic table here, 12.01 atomic mass units. So 1 carbon atom has a mass of 12.01 atomic mass units. So if we just got the mass of this entire sample, we can just do the same thing we did here and divide to get the number of carbon atoms we have. Okay, so here we're actually going to do that. If the above sample of carbon has a mass of 25.6 grams, how many carbon atoms are present? So in order to do this, we need 1 conversion factor, and that's 1 atomic mass unit is equal to 1.66 times 10 to the minus 24 grams. Okay, so atomic mass units is a mass scale. Grams is another mass scale. So now that we have that, we can solve. Okay, so we're going to use just simple dimensional analysis here. 25.6 grams of carbon. Okay, so units of grams isn't going to be helpful because we're going to need to use one carbon atom and the mass of that carbon atom. Okay, so we're going to turn grams into atomic mass units. So we have 1 AMU up here, 1.66 times 10 to the minus 24 grams. Okay, so that gets our grams to cancel. Now if we do this conversion right here, we would have the mass of this pile of carbon in units of atomic mass units. Okay, so now we're going to use this relationship here between the number of carbon atoms and the mass to find now the mass or the number of atoms of carbon we have here. So up here we're going to put that one carbon atom has a mass of 12.01 AMU. So now AMU cancels and AMU cancels, and we're left with just units of how many atoms we have. Okay, so let's grab a calculator. Okay, so we have 25.6, divide that by 1.66 times 10 to the negative 24. Okay, so that's my first. And then we're going to take that and divide by the mass of our carbon atom, our 12.01. So when we do that, we get that we have 1.28 times 10 to the 24 carbon atoms. So if we were able to take this sample of carbon and count the individual carbon atoms, this would be what we have, 1.28 times 10 to the power of 24 carbon atoms. So it's a lot of atoms. This would, take you a really long time to do. In fact, I don't even think you could really do that. Okay, so what this shows is we have a mass of carbon, and we can use the fact that we know one carbon atom's mass to see how many carbon atoms would be in a different mass by using counting by weighing. Okay, so this has a few shortcuts, and the rest of kind of what we talk about below here is going to be a little bit of shortcuts for this process here. Okay, so the first shortcut we have is defining the term mole. So we're going to define the term mole. So a mole is when we have an Avogadro number of something. So what a mole is, 1 mole equals 6.022 times 10 to the 23 of something. So 1 mole equals 6.022 times 10 to the 23 of something. So this kind of seems like a sort of a random number. This is called Avogadro's number, this one right here. Where this comes from is based off of our mass scale. So up here we had 25.6 grams of carbon, and we looked at all of this here, or we did our conversions here, and we got the number of carbon atoms. So Avogadro's number comes from is taking the mass of an atom and making it so that if we had 12.01 grams, we'd want to know how many atoms does that equal. Okay, so if we took the mass in AMU and we wanted to know the mass in grams of that object, so again, this mass could represent carbon on a larger scale in terms of grams. That's where Avogadro's number comes from. So for example, if we look at, again, our small scale, where we have 1 carbon atom, and we said that we have the mass of 12.01 AMU. Okay, so that mass equals carbon atom. So what they did on the larger scale is said, you know what, since we have this number that represents carbon, we want that to represent carbon all the time. So we're just going to take this AMU and bring it to a larger scale of grams. So 12.01 grams. So now the question is, for one carbon atom to get 12.01 AMU, how many carbon atoms would we need to bring that number into from AMU to grams? Okay, so if we look, we wanted 12.01 grams. We're going to do the exact same conversion. So 1 AMU per 1.66 times 10 to the minus 24 grams. And then for every one carbon atom, we have 12.01 AMU. Okay, so if we do this conversion, 12.01 divided by 1.66 times 10 to the minus 24, and then divided by 12.01 again, we get Avogadro's number. So 6.024 times 10 to the 23rd. Okay, so this is Avogadro's number. Okay, so where this, you need Avogadro's number of carbon atoms to go from atomic mass units to grams. And this isn't true for just carbon. You could take this, for example, if we wanted to look at another element, like for example, I don't know, how about silver? So silver is 107.9. So if we looked at silver instead of carbon, this would be 107.9 grams. This would be 107.9 AMU. And if you went through and you did the math, you still get Avogadro's number. Okay, so Avogadro's number is a way to go from looking at the mass of an individual atom in AMU to take those AMUs into grams, and how many atoms would you need to represent that in terms of grams. Okay, back to our worksheet here. So kind of looking to do, so a mole is going to be our shortcut. So the shortcut for Avogadro's number is that our 1 mole equals 6.022 times 10 to the 23rd of the object. So if we go back on the back here, okay, so for our going from AMU to grams, Avogadro's number, or 1 mole. So 1 mole of any atom will give you the mass of that atom in grams instead of AMU. And we call that the molar mass. Okay, so the molar mass is the mass of an element, compound, ion, etc. of exactly 1 mole. So if you have exactly 1 mole of the element, compound, ion, whatever, the mass of that is defined as the molar mass. So the units of molar mass are grams per mole. So molar mass is in units of grams per mole. So kind of using what we did on the back of this sheet here, we look at the periodic table. Like for example, our nitrogen at 14.0067. This could be the mass, the average mass of 1 nitrogen atom in AMU, or this could be the molar mass of nitrogen at 14.0067 grams per 1 mole of nitrogen, or grams per mole. So now the units for our atomic mass here can be for in AMU if you just have 1, or again, if you're looking at an entire mole, then this mass now is in units of grams. Okay. So now if we look, how many moles of carbon are in the 25.6 grams above? So I'm going to do this 2 ways, where we can kind of use our definition of molar mass and our definition of the mole. Okay, so the first way, we're going to take our 1.28 times 10 to the 24 carbon atoms, and we're going to use the definition of the mole, where 1 mole is 6.022 times 10 to the 23rd. Right? So 1.28 times 10 to the 24 divided by Avogadro's number gives us we'll call it 13. So 2.13 moles of carbon. Okay, so we can use our definition of molar mass to do the exact same thing. So in this one, we would take our 25.6 grams of carbon, and we would use the definition of our molar mass, where we have the mass from the periodic table that equals 1 mole. And in this case, we would have 1 mole of carbon for every 12.01 grams of carbon. And we will get the same thing. 25.6 divided by 12.01 gives us that same 2.13 moles of carbon. Okay, so we can get there either way if we have the number of atoms using our definition of the mole from Avogadro's number, and if we have the mass, we can use our definition of molar mass to do that as well. So let's do a few practice problems with mass and molar mass. So depending on what's given, we'll use either our definition of moles with Avogadro's number, or we can use the molar mass. So here they're asking what is the mass of 3.50 moles of sodium atoms. So they're asking us to go from moles to mass. So to convert from moles to mass, so we will use our molar mass here because that is relating moles and mass. Okay, so we have 3.50 moles of sodium. So we're going to look up our conversion factor here. So sodium is 22.99. So 22.99 grams of sodium for every 1 mole of sodium. So moles cancels. Okay, so if we multiply through 3.50 times 22.99, that gives us 80.465. So we had 3 sig figs, so we're going to do the same here. We'll call it 80.5 grams of sodium. Okay, so next, how many moles are in 56.8 grams of sulfur atoms? Okay, so now they're asking us to go from grams to moles. So kind of a similar thing we had here, moles and mass, same thing, now we're going mass and moles. So again, we should probably use our molar mass because it relates our grams and moles. So we have 56.8 grams of sulfur. Okay, let's look at our periodic table. Sulfur is 32.065, so we'll call it 32.07. So 32.07 grams of sulfur for every 1 mole of sulfur. So now since I had grams and I'm going to moles, I'm going to divide by the molar mass. Going from moles to grams, I multiplied. When I'm going from grams to moles, I'm going to divide. Okay, so punch this in our calculator, 56.8 divided by 32.07 gives us 1.77 moles of sulfur. 1.77 moles of sulfur. Okay, so the last one in our practice section, how many grams of argon atoms are present in 25.78 grams of argon? So how many argon atoms in this particular mass of argon? So now we're being asked to go from mass to number of atoms. So we'll probably do this in 2 steps. So I have a conversion to go from grams to moles. So I'm going to go from grams to moles using our molar mass, similar to what we did up here. Once I'm in units of moles, I have a conversion factor to go from moles to number of atoms, and that's using Avogadro's number. So we're going to start with our 25.78 grams of argon. So I'm converting it to moles. So I'm going to end up dividing by my molar mass like we see here. So we're going to put our 1 mole of argon up here. So the mass of argon we're going to get from our periodic table, 39.95. Okay, so grams of argon cancels with grams of argon. So we're left with moles. And now to go from moles to number of atoms, we're going to use Avogadro's number, where we know 1 mole of argon equals 6.022 times 10 to the 23rd argon atoms. Okay. Let's punch this in. We have 25.78 divided by 39.95. So that's our number of moles of argon. And now we're going to multiply this by Avogadro's number. So we have 3.886 times 10 to the 23rd argon atoms. Okay, so using Avogadro's number, using molar mass is counting by weighing. If we have the mass, we can figure out how many atoms we have. But oftentimes, we're going to use this a fair amount in this chapter. As we move from this chapter, the preferred unit of how many is moles. So you're going to see moles, and we're going to use moles much, much more than we are here. It's a shortcut. It's much easier to deal with units of moles where you have like 1, or in our example here in my calculator, where we had 0.6453 moles of argon. So dealing with, again, a number like this is much easier than having to deal with a number like this. So moles is our shortcut, okay, where we can have a much better number than this one with the very large exponent here. So we're going to see moles much more often. Okay, so to finish this lesson up, we'll look at how this applies to compounds, and then we'll save the last of this for another lesson. Okay, so now let's expand this to compounds. Explain how you'd find the molar mass of a compound like NaCl or Fe2 So4 3. Okay, so how would we find the molar mass? So how we're going to do this is just add the mass of each atom present. And that's all we have to do. If we have a compound like NaCl, we're just going to take the mass of sodium and add it to the mass of chlorine. And for something more complicated like iron 3 sulfate, we're just going to add the mass of every single atom present there to get the mass. Okay, so let's do that. So for NaCl, start with the easier one. So sodium, here we have 22.99. grams per mole. And then we have 1 chlorine, so 35.45. . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . 35.45 . Okay, so we're going to add those two together. Okay, so 22.99 plus 35.45 gives us 58.44. So for a compound, we wanted 1 mole of sodium chloride. We would need to weigh out a mass of 58.44. So 58.44 grams would give us 1 mole of sodium chloride, or it would give us 6.022 times 10 to the 23rd sodium chloride compounds. Okay, number 2, now we're going to find Fe2 So4 So this one is a little more complicated, lots and lots of atoms here. So Fe2 So4. Okay, so this means we have 2 irons. So we're going to do 2 times the mass of iron. So that's 55.85. Then we're going to add that to, if we look at this 3, this sort of distributes into the sulfur. We have 3 sulfurs. So 3 times, we use sulfur up here, that's 32.07. And then finally, we have 4 oxygens in a sulfate, but we have 3 sulfates, so 3 times 4 gives us 12 times the mass of oxygen, which is 16.00. Okay, so let's add this up. We have 2 times 55.85 plus 3 times 32.07 plus 12 times 16. So this gives us 399.91 grams per mole. Okay, so this compound, much larger, 2 irons, 3 sulfurs, and 12 oxygens. So to get 1 mole of this very large compound, we need almost 400 grams to get that 1 mole. So it's a lot larger because it has 3, 4, 5, plus 12, 17 different atoms that make up this compound. So its molar mass is quite a bit larger. Okay, so let's finish this off with practice problem number 3 here. How many moles of chromium-3 nitrate are present in 33.7 grams of the compound? Okay, so in order to do this problem, we need to figure out what a chromium-3 nitrate is. So chromium is Cr. That 3 tells us it's Cr3+. A nitrate is a NO3-. Okay, so if I were to combine these to make a neutral compound, we have CrNO3 3. Okay, so let's find the molar mass. If we're going to be converting between moles and grams, we need the molar mass. So for compounds, we can't just look on the periodic table like we can for elements. We actually have to calculate it. Okay, so chromium, we'll look him up. 51.996, so we'll round it to 52. So 52.00 plus 3 nitrogens, which are 14.0067, so we'll call it 14.01. And then 3 times 3 gives us 9. Oops, that's a 6. And we had oxygen above at 16, so 9 times 16. Okay. So let's see what we have here. So 52 plus 3 times 14 plus 9 times 16 gives us 200 and, oh, here I didn't have my decimal points for my nitrogen, 14.01 plus 9 times 16. There we go. Gives us 238.03 grams per mole. Okay, so now that we have the molar mass of our compound, we can do the conversion. So it's exactly the same as we did with our elements. We're going to set it up in dimensional analysis to get things to cancel. So we have mass of chromium nitrate in the numerator. So when you're going from grams to moles, we always end up dividing by the mass. So that's our 238.03 grams of chromium nitrate. And that 238.03 is for every 1 mole of chromium nitrate. Okay, so we have 33.7 divided by our molar mass, which we just calculated. So it gives us 0.14157. If we look, we had 3 sig figs here, so we're going to round this to 3, so 0.14, and then we'll round this to 2, so 0.142. So that's how many moles of chromium nitrate we have. So the process was exactly the same as when we were looking at just having our elements. The only difference was we could look up these molar masses from the periodic table. When you have a compound, all the definitions are the same, all the rules are the same. The only difference is you're going to have to calculate the molar mass before you can convert from grams to moles. So this stuff that was on this paper here, this practice, this is extremely important. We're going to be doing this pretty much in every single chapter for the entire rest of the semester. So definitely make sure you are good and comfortable with this, and that you are good and comfortable with doing this down here. Because like I said, we're going to be doing this. This is one of the most fundamental sort of tools we use in chemistry, and we're going to be using this quite a bit.